classical gravity, and to some, for us, still open questions that exist in the cases when there are internal boundaries and that we want to understand. So in collaboration with Alejandro Corici and Hamiltonian Reyes, we were working in understanding how to give consistent canonical formulations of the theories that have boundaries. So one example is the theory of gravity, and one example of the boundary is a weakly isolated horizon. So last year I presented at some other event our advances in this area in the case of non-rotating horizons, and today I would like to talk about rotating ones. But first I will define what are rotating weakly isolated horizons. Then I will give the theory that we are working in, and then consider horizons as an internal boundary in the definition of the theory. And then talk about these two different Hamiltonian approaches, covariant and canonical one. And covariant one actually is completely well understood and elegant, and canonical also is really nice, but this is the part that we are working on now, actually. So weakly isolated horizons are generalization of Killing horizons, of event horizons, and they model black holes in equilibrium, even in the cases when the space-time is not symmetric, or in a sense that it does not admit any Killing field. So Killing horizon, weakly isolated horizon actually, is a null surface, null hypersurface, when we have a family of null vector fields that define this surface, and they are geodesic, they satisfy the geodesic equation, and the kappa, this non-affine parameter, is what we call usually surface gravity. So if we want to define a horizon, then we have to restrict, of course we have to put some restriction. So we suppose that this null hypersurface is diffeomorphic to S2 cross R. The other very important and defining characteristic of the horizon is that the expansion of any non-normal vanishes. That makes it really isolated, so there is no, the matter, nothing can enter the horizon. And that Einstein equations hold when the stress energy tensor satisfies certain conditions. We'll consider theory in vacuum, so we will not these conditions for energy momentum tensor are not so relevant here. So it turns out that when we are dealing with null hypersurfaces, then we have to be just to learn how to deal with them. And it turns out that if the expansion of the null hypersurfaces vanishes, then we can define the one form, which we call the rotation form omega, in such a way that is given here. It turns out that this is a part of the connection induced on the delta, on the horizon. When I put this arrow beneath the index, it means just a pullback to the horizon. And when we have for example, example, this kind of notation means that it's something that is valid on the horizon. Sometimes I forget to put them. I just put this picture in order to be able to visualize better what is the meaning of the various objects that we have defined on the horizon. But they're clearly defined in terms of another tetrad. So our horizon is generated by L, and we can define 3 more null vector fields in order to have a basis in the space-time. So we have a pullback metric to the horizon, which is a degenerate one, transfers area to form, which can be expressed as here, this rotation log form that I mentioned that will play a very important role. And also this transverse connection log form that will also play a role in this approach. So the part that is important is that we have this metric, that we have actually a connection on delta, which is not completely defined by a metric because delta is a non-hypersurface. And we have these parts of the connection that are encoded in these 2-1 forms omega and v. So it turns out that it's still not enough to define a weakly isolated horizon. But all these subjects about weakly isolated horizon, about isolated horizons arise more than 20 years ago. And there was an additional restriction that the whole connection induced on the horizon should be invariant along the horizon, should have a symmetry along the horizon. So later this type of horizons were called strongly isolated horizons. Then it turned out that this condition can be relaxed in order to permit more metrics. And this notion of a weakly isolated horizon was introduced when we only demand that the part of the metric, this omega, this 1 form omega, is preserved, does not change along the horizon. And we also need to fix a class of non-normals, and any 2 normals in this equivalence class are just multiple one of the other with a constant coefficient. Then it turns out that this condition on the omega implies that kappa, the surface gravity, is constant on the horizon, which is a zero law black hole mechanics. Now, if we are interested in rotating horizon, then we also have this axial symmetry. So we have an additional vector field on the horizon that generates rotations. And in order to be a symmetry of the horizon, it should satisfy these conditions that I put here. So rotating isolated horizon would be like a non-hypersurface whose expansion equals to 0, equipped with this class of non-normals, and with actually fixed generator of rotation. So, as I said, the idea is of the isolated horizon was that we really don't need the space-time. The whole space-time has some symmetry, but we just need the horizon possess. Okay. So then I would like to show you the way to obtain the expression for the mass and angular momentum in this case. And they are related to the Hamiltonians that generates symmetries on the horizon. So here, like our starting point was this action for gravity in self-dual variables that are solver inform and self-dual connection, spin connection, and they have to satisfy some certain boundary conditions in order to be compatible with the existence of a weakly isolated horizon. So we will consider spacetimes that have boundaries. They are, for example, they are asymptotically flat configurations. They have a weakly isolated rotating horizon as an internal boundary, and they have also this, well, in the covariant formalism, they will have this initial and final Cauchy surface. So in covariant formalism, we have a covariant phase space, which is formed by the solution of all the solution of the Einstein's equations that have an isolated horizon as the internal boundary. And our case, as I said, is our action is this one. But it turns out that everything that we did at some point for the Hall action reduces to this case when we just take the gamma equals I. So we can just take some results that we obtained earlier for the Hall action. And one of them is, for example, that the Hall term that is added to a Palatini action does not contribute to the symplectic structure. So actually the symplectic structure or in the covariant phase space, which is like an important object that we need in order to define the Hamiltonians, has two terms. One of them is defined in the bulk and the other on the boundary. And the part in the boundary is exactly the same as in the case of Palatini. So now I will just remind you of the results of this paper of Ashtekar, and Lewandowski that they did like more than 20 years ago about weakly isolated rotating horizon in this formalism in covariant phase space. So the idea is, as I said, to define energy and angular momentum as Hamiltonians that generate symmetries of space-time. So the basic equation for that is actually this one, that the variation of this corresponding Hamiltonian is given by actually by the symplectic structure of the theory. And here it turns out it's very in a way it was curious for me at the beginning, but then it's understandable. When we take that these vectors on the phase space, covariant phase space, delta W are actually Lie derivatives of the field. Then it turns out that the boundary covariant structure does not contribute at all, and that the bulk symplectic structure reduces to a total derivative. So it goes its contribution goes completely to the boundary. That part is not surprising because the Hamiltonian lives on we know the Hamiltonian will live on the two sphere, which is an intersection of the Cauchy surface and delta and in the horizon. But the surprise for me was that this boundary term in the symplectic structure does not contribute at all by itself. So that was a nice result that they had, and in order to define the energy of the horizon, one has to construct a Hamiltonian that generates a time evolution of the system. And so they start with with an evolution of vector field T, which is just at the beginning the combination of L and P, the symmetry generators of the symmetry on the horizon, and just putting it here in this expression for the variation of the Hamiltonian, they arrive to the first law of mechanics of black holes in this case. And so we have a contribution of area of and kappa, and also, of course, the contribution of the angular momenta that is defined in this way. So everything is very elegant and fast, in a very fast way to obtain these conserved quantities. But it turns out that T that was originally completely arbitrary cannot actually be arbitrary. It must be just chosen in that way that it leads to this first law. And there are also some consistency condition that H, the corresponding Hamiltonian, or that correspond to the energy of a horizon, that it exists only if this relation is satisfied. Well, here the important point is that they prove that kappa, which is a surface gravity, and omega, which is angular velocity, only depend on the area and angular momentum of a horizon, of a black hole. So very nice result. And there is a way to define the mass of the horizon, choosing in a special way this evolution vector field in a way that it coincides with the vector field that one would obtain in, for example, in K metric, which is a stationary symmetry. Well, what happens in the canonical approach? So the starting point is a canonical action, and the first part so one has to do a 3+1 decomposition of the fields, and in this case it's relatively easy to do it because the pullback of the connection of the four-dimensional connection to sigma, to the Cauchy surface, is again a connection. So that's a nice property of this action in self-dual variables. And we have this usual kinetical part in the action, which lives in the bulk. And we have these parts that are just combination of constraints of the theory, plus a boundary term that we obtain in, because we need to do some integration by parts. It turns out that the boundary term is of this form and can be calculated for the horizon. So when we started to do this, first we started with non-rotating horizons, and we saw that this boundary term could be could be treated just like this, like the boundary term in the Hamiltonian of the theory, or can be rewritten as a kinetical term on the boundary, on the horizon, by introducing some appropriate potentials, which is, for example, what was done in the covariant case and what we also did in canonical one. So it can be seen as a boundary term in the Hamiltonian, or as a boundary term in the symplectic structure, or the mixture of both. So for us, it was a kind of interesting to explore different these different possibilities and see what they meant in that case. And in some cases, we obtained like a symplectic structure with a boundary term that includes this potential V and an appropriate expression for the energy of a black hole. And in some cases, for example, the Hamiltonian didn't have any boundary terms, so then we didn't know how to calculate the energy. And so we were just like exploring what happened. And then we just wanted to see what happened in the case of rotating horizon. So in the difference between the covariant case, in covariant case, of course, a covariant phase space is space of the solutions. So the Hamiltonian that defines the energy is from the beginning defined on the two sphere. Doesn't have any bulk contribution. Here, the Hamiltonian has a bulk contribution and also a boundary term. So in this first approach to the problem, we just decided to try to do a rigid dicarbon, which means just to allow functionals whose functional derivatives on the boundaries vanish, and try to see what happens. And when one starts with a generator of diffeomorphism and choose as a vector field exactly this generator of rotation, then one can easily see that there is an additional, there is a term on the boundary in the derivation, in the variation of the diffeomorphism constraint. So in this standard rigid dicarbon case, one needs to add a counter term in order to annul the contribution of this variation. And it turns out that this counter term is exactly what is expected to be an angular momentum. So on shell, let's say, we have a generator is actually just the angular momentum. Then, of course, we try to do the same for the energy, taking the same T evolution vector field T, which is a combination of L and C. We arrived to a quite simple expression for the variation of this Hamiltonian, we are like trying to construct a counter term. That was the idea. And in turn, this counter term depends on the free parameters of the horizon. one starts from this like general expression and analyze its variations, and then one can prove that a counter term actually only depends, or usually depends on the area and angular momentum of the horizon. So in order to have a well-defined Hamiltonian, then we have to annul all the boundary contributions in the variations of the Hamiltonian plus a counter term, and it leads us to a set of partial differential equations for this function. So, as I could here, the final result, of course, should give us what we know from the covariant approach, but we still cannot, arrive to that result. We still don't understand what is happening. And also, here, there is still a question, is boundary term in the symbolic structure necessary for the consistence of the theory, or is because in a way it's arbitrary for a moment at the classical level, and is it necessary here or not? What we discovered in the non-rotating case that if we don't have it, then we have to fix some gauge symmetry that we have, and in some cases we can obtain even a la Regge Teitelbaum a good expression for the energy in non-rotating case. Here still this is a work in progress. So these are, Fernando Valero in his book, you're working a lot about with theories defining regions with boundaries. With another approach, I just put one of the first papers that you did, and we did various papers considering the different theories defining regions with boundaries in order to extract the impact of the boundaries in the canonical formalism especially. Well, thank you.
And now it's time for questions. Do you have some questions?
So given the papers which you referred to, those which Amayashkar and people which
Yes.
in the early 2000s,
Yes.
what is this problem that you were trying to solve, that you didn't solve? Or?
No, you did, but in the context of a covariant phase space. So we wanted to see what is happening in the canonical formalism, like if we can reproduce the same results, and because maybe this is a better starting point for a quantization of the theory. So that was like the motivation, to try to understand if they lead to the same answers as they should. But we found something that was like surprising to us, that for example, this symplectic structure on the boundary does not coincide in the covariant case and in the canonical one, and we still don't understand why. So these are maybe technical things, but that's what are we trying to understand. And not only in this theory, this is an example, but like in a general one with a boundary.
There was a question about this.
I understand that you need only local characteristic of the horizon. You don't care about whether this is absolutely flat or not.
For this
Yeah.
talk, no.
No. Okay, but assume that you know that your horizon is in asymptotically flat space-time. What would be the relation between the angular momentum, the asymptotic angular momentum, and the local one? Can you say anything about it?
Well, we actually, Lewandowski would be like a better person to answer that because they did it in that paper. They showed that it's the same. Actually, it's the same, the angular momentum on the horizon.
The same, this is a kind of a vacuum extension because one can imagine.
Well, for example, the energy is not the same because the energy can have a contribution from the radiation. So the other energy at the infinity, it's in general not the same as the energy of the horizon. But the angular momentum is
okay, so
the same.
I should ask you after his lecture.
Yes.
Okay,
The condition is that this field phi should tend to a corresponding symmetry, axial symmetry generating field in the asymptotic region. But they turned out to be the same, which is also interesting.
Okay, so that's kind of